Welcome to Etch Processes for Microsystems Fabrication, Part 2, presented by SCME, the Southwest Center for Microsystems Education. For information about SCME, please visit our website at scme-nm.org. In Part 1 of Etch Processes for Microsystems Fabrication, we talked about the different types of etch processes, surface and bulk, wet and dry. We went into detail on the wet etch processes. In this presentation, we will discuss the dry etch processes, as well as the differences between chemical and physical etching. In dry etch process, a single wafer or a batch of wafers is placed in a sealed chamber and then exposed to a gaseous etchant which is suspended in an RF or radio frequency energized plasma. Collisions between the gas molecules and energized electrons create a soup made up of electrons, ions, and radicals. Each of these particles have a definitive purpose, as we'll discuss in this presentation. By design, dry etch methods provide more control over the factors which influence etched results. Dry etch processes provide directional control of the etch, anisotropic profiles, and greater control over the process parameters such as pressure, temperature, gas flow, and power. This control allows very detailed and specific etching to be performed. Because gases are the primary etchant and are housed in a sealed chamber, human exposure to dangerous chemicals is limited. However, the equipment is very expensive to purchase and just as expensive sometimes to maintain. Dry etch is normally used to remove selected areas from the surface layer rather than bulk material of a substrate or a sacrificial layer. Dry etch can be a chemical etch, a physical etch, or it can be a combination of both. Physical etching is similar to sandblasting, where high-velocity sand is used to chip away at an exposed surface. In sandblasting decorative glass, a picture such as the one shown here is formed on a sheet of glass using a strong protective material. This material stands up to being blasted with high-velocity sand particles. The unprotected areas of the glass are etched by the sand, which removes particles of glass from the surface. When the desired depth is reached, the blasting stops. The mask is removed and the design is exposed. Physical etch is very similar to this. Instead of sand, positive ions created by collisions in a plasma bombard the surface of a wafer, causing molecules to sputter off the surface. The hard mask on the wafer surface protects the areas that we don't want etched. In this image, the hard mask is the photoresist. Notice how the photoresist protects areas of the silicon nitride while exposing other areas. The silicon nitride is etched wherever there is an opening in the photoresist. In this image, the photoresist has been removed to show the patterned silicon nitride layer. If you watched Part 1 of etch processes, you'll know that the silicon nitride pattern identifies the area of silicon that are to be etched later on in a wet chemical process. Like sandblasting, physical dry etch is an entirely physical process with no chemical reaction occurring. So let's see how this works. Wafers are placed on a negatively grounded holder in a vacuum chamber. A gas is introduced into the low-pressure chamber, which is usually less than 50 millitorr, or down into the high vacuum region. RF power is applied to the chamber, and a plasma is struck. In the chamber, the gas molecules pass through the plasma and collide with high-energy electrons. The energy is transferred from the electrons to the gas etchant molecules. These collisions result in high-energy state positive ions as well as free radicals. These positive ions are attracted to the negatively charged cathode where the wafers sit. The ions accelerate as they move toward the cathode. When the ions hit the wafer, surface layer molecules are sputtered off the surface. This process continues until the pattern is etched through the surface layer, exposing the underlying layer. As I mentioned before, the plasma consists of electrons, ions, and free radicals. The ions are used for physical etching, while the free radicals are used for dry chemical etching. Free radicals are atoms or molecules that have at least one unpaired electron and are therefore unstable and highly reactive. It is the free radicals that react with the surface, creating volatile particles that are released from the surface and then removed from the chamber. This process is called a dry chemical etch. Chemical etching requires a gas etchant that will chemically react with the wafer surface layer. Free radicals of this etchant are generated in the plasma, and once produced, they travel towards the wafer where they are absorbed by the material on the wafer surface. A chemical reaction occurs between the material to be etched and the radicals. Byproducts of this reaction desorb from the surface and diffuse back into the plasma. The outcome of the chemical etching is an isotropic etch, usually with undercutting, just like we saw with wet chemical etchings in part 1 of this series. The dry plasma etch process uses two primary parameters to control the type of etch that takes place, whether the etch is chemical or physical. The parameters are process pressure and RF power level. This chart shows how these two parameters affect the type of etch. Chemical etching at the wafer surface can be increased by increasing the process pressure or decreasing the RF power level, or both. Of course, for any chemical reaction to occur, one of the plasma gases or etchants must be reactive with the material to be etched. With physical etch, the amount of physical etch increases with a decrease in chamber pressure and/or an increase in RF power. By carefully controlling these two parameters, you could have all physical etch, all chemical etch, or a combination of physical and chemical etch. This control allows for specific shapes and sizes to be fabricated. Regardless of the technique used, wet etch or dry etch, physical or chemical, the etch quality is influenced by several factors. A few important factors for microsystems include etch rate, directional control, and selectivity. Etch rate is the rate at which the material is removed from the wafer. In other words, 50 angstroms per minute or 5 angstroms per minute. The faster the etch rate, the faster the material is removed. For instance, 50 angstroms per minute etches faster than 5 angstroms per minute. Directional control results in achieving the desired shape through the type of etch profile, isotropic, anisotropic, or a combination of both. As you've seen, different types of etchants results in different profiles. Selectivity is the property of the etchant which permits it to selectively etch specific materials at a faster etch rate than other materials on the wafer. Selectivity is the ratio of the etch rate of the material to be etched to the etch rate of the material not to be etched. For example, if we refer back to the backside etch for the MEMS pressure sensor, which we talked about in part 1 of this series, we need to use a mask that can withstand the wet potassium hydroxide etch, which can last up to 4 hours. This process has to etch all the way through the silicon. Therefore, we want the masking layer to be basically non-reactive with KOH, or potassium hydroxide, or to have a very, very low etch rate relative to the etch rate of silicon. So to make sure that you understand selectivity, I have a question for you. You saw this picture previously, and I mentioned that it was an etched silicon nitride mask that would be used in a wet chemical etch to etch exposed silicon. The wet etch process uses potassium hydroxide, or KOH, to etch the silicon. This particular etch process can take up to 4 hours. Therefore, we do not want the silicon nitride layer to be removed or etched away before the silicon is completely etched through. So in thinking about the term selectivity and comparing the etch rate of silicon to silicon nitride, what would our selectivity ratio ideally be? Very low or very high? You can pause this video and think about the question for a moment. If you said that we want a high selectivity, you are correct. A high selectivity means that with a correct timed etch, the material to be etched, which in this case is silicon, can be completely removed before the masking layer of silicon nitride is even affected. Now let's take a look at etch rate. In the SCME Etch Learning Module, we have an activity that is supported by a kit called the Rainbow Wafer. One part of this activity is to estimate at least 6 oxide thicknesses on a wafer, graph the relationship of the amount of oxide removed, or the oxide thickness, versus time, and calculate the etch rate. This chart is an example of the relationship between the amount of oxide removed and time. The x-axis is time and the y-axis is oxide thickness removed. As you can see, it shows that the longer the etch, the more oxide is removed. Using the information on this chart, we can estimate the etch rate in angstroms per minute by determining the slope, or rise over run, of the line. The line you see is the line of best fit for the data points that were gathered. Take a moment and determine the etch rate of this process. Again, the etch rate is basically the slope of the line. If you said 300 angstroms per minute, you are correct. As you can see from the graph, at 6 minutes, 2,000 angstroms have been removed, and at 4 minutes, approximately 1,400 angstroms have been removed. So therefore, that is a difference of 600 angstroms. The time has a difference of 2 minutes, so 600 angstroms removed over a 2-minute period leaves an etch rate of 300 angstroms per minute. Another type of dry etch is reactive ion etching, or RIE. RIE uses mid-level RF power and mid-range pressure to combine both physical and chemical etching in one process. The positive ions from the plasma bombard the wafer surface at the same time that the radicals are absorbed to the surface. You remember that we can control the etch by adjusting the process pressure and RF power so that we can get both types of etching, physical and chemical, occurring at the same time. This process provides high selectivity ratios. It also produces anisotropic profiles on features less than 3 microns wide. Its ability to capitalize on the advantages of both physical and chemical etching makes RIE an invaluable tool in the manufacturing of microsystem components. A special subclass of RIE is deep RIE, or DRIE. Deep reactive ion etching is used to etch deep cavities or trenches in substrates with relatively high aspect ratios. These cavities can be hundreds of micrometers deep while only a few micrometers wide. Aspect ratios up to 50:1 can be achieved with DRIE. As new DRIE methods are developed, it is very likely that these aspect ratios will get even higher. This scanning electron microscope image, or SEM, shows a series of cavities etched using a DRIE process. Notice that the deeper cavities have the wider openings. This SEM shows that one of the ways to control cavity depth is by controlling line width. In addition to creating cavities, DRIE can be used to create tall, thin objects or components for microsystems devices. These objects can later be released through other etch methods such as wet etching. The SCME shows a leaf spring created by DRIE. Notice how the spring is attached to a block at one end, the front, and to a slider at the opposite end. The entire spring has been released from the substrate, allowing it to expand and contract. So as you can see from this presentation, dry etch processes have enabled the construction of very unique components with low to high aspect ratios that can be used throughout microsystem devices. For more detailed information on these etch processes, be sure to download the Etch Overview Learning Module from the SCME website under Educational Materials. Both Part 1 and Part 2 of etch processes are available through YouTube and are online at the SCME website. Thank you for viewing this presentation produced by the Southwest Center for Microsystems Education.